afterwards some additional time for discussions during the break. Going to go with HDMI or the HDMI?
No, it's not HDMI.
Yeah, well.
VGA.
Oh, VGA. Okay. Good.
Okay, so hello again. I am still Antonio Virdis, and I will guide you towards the next coffee break with a tutorial about SimuLTE. This tutorial is partially based on our work simulating device-to-device communication in OMNeT++ with SimuLTE, which I wrote with Giovanni Nardini and Giovanni Stea, both of them from University of Pisa as well. Quick outline of what we will talk about. I will give you a little bit of context about LTE. I will present you the simulation structure, basic simulation structure, and we will go through 3 examples, like trying to follow a very simplified history of LTE from since the beginning towards the last developments. So, based on my experience on almost every communication conference about information technology in the world, there was always at least one guy talking about LTE. LTE is basically my basic experience, and for today I am that guy. And we will have to talk about a little brief background of LTE. LTE is a cellular technology whose main actor is called eNodeB. It's the well-known base station which controls almost everything that happens within a cell. The other main actors are, of course, the cell phones, which are employed by end user to communicate. And those are always one endpoint of each communication. They have to communicate always with eNodeB, whose role is to coordinate and control every kind of communication. They communicate with him both in this direction, which is called uplink, and the other way up, that is called downlink. And basically, from an high-level point of view, what happens is that user equipment are communicating to the eNodeB the data rate, data requests, and the channel quality they perceive, which basically implies which is the actual data rate at which the communication will take place, the maximum data rate for the communication. And the eNodeB in turn performs scheduling. Okay, so receive all this information and decide who is going to talk on which resources and who's going to receive information in other resources. Okay, so this is a quite big picture of this. But why LTE is becoming so important these days? First of all, it's an all IP network, completely IP. Everything that runs on top of LTE is IP, even for the voice part. So it's basically all the phone calls are VoIP calls. And second, I just forgot to mention that all those we are seeing happens at 1 millisecond pace. I will get back to this later. But the second important thing is that being all IP is actually being employed for in a lot of scenarios, starting from IoT scenarios or sensor networks in general, vehicular technology as well for letting cars communicate, and even recently for managing drone flights, okay, for coordinating drone flights. And those are some of the reasons why this is widely being used. So within this context, SimuLTE is a system-level simulator for LTE networks, which of course is based on OMNeT. It is focused on testing and implementing and testing resource scheduling algorithms. So our main focus is not evaluating the channel quality on the channel characteristic, but evaluating algorithms that will run basically from layer 2 and upwards. And it's completely INET based, so it reuses almost everything that can be used from INET is reused, and can be interconnected with mostly, I think, most of the elements from INET, and is built in as an additional network interface, so it can, it supposedly can be put in any other existing compound module. It's something that actually has been made by Vane's guys, something like this. And is developed in order to follow the evolution of the cellular communication, because they are adding quite a few new features from time to time, so we have to kind of follow these new features. So how we implemented it? As I said, the user equipment is one end of each communication, but what about the other hand? The other end is generally some kind of node within the internet, and by reusing the elements given by INET, we can use, for example, standard hosts, which are standard INET hosts, which are connecting via routers or any kind of networks to the node B, and so in either directions, they can use this network to communicate. So this is all this in red is standard INET. And from the point of view of the LTE nodes, we have an implementation that is pretty similar, again, to the standard host from INET. So all the upper layers are the same. So we have application, UDP and TCP application on top, and UDP and TCP, for example, protocol layers, the IP standard layer, and then, as I said, we have an additional NIC card. Just for completeness, I saw some work which used other NIC card altogether with the LTE NIC card one, for example, using Wi-Fi cards as an alternative to that. So once this is defined, we go into the LTE NIC card. The LTE layer, as you can see, is pretty simple. These three layers are the sub-layers that are implementing layer 2 functionalities, and I will not go into detail of this. And the physical layer is responsible for modulation and coding and stuff like that. Data flows in both directions, as I said. And when we implemented our NIC card module, we tried to follow the same structure as for the layering. Using each one of these is a simple module which is part of the LTE NIC, which is compound one. Again, the data stream flows in both directions. Actually, what happens is that it follows the communication paradigm of OMNeT, of exchanging messages between modules, but everything stops at the MAC layer here. Okay? Because, as I said before, everything in LTE works at 1 millisecond pace. So the messages are flowing through the network, and when they reach the MAC layer of any node, they are blocked in there. Okay? So it's basically a quantization of time on a 1 millisecond base, which is exactly what is happening within LTE. Okay? And as we can see, this is where it is placed. The next, how we actually implemented this, every element that we saw takes part of something that we call the NIC card, of course, and we have a base implementation which is common for both eNode Bs and user equipment, and we obtained a specialized version for both nodes via inheritance. Same thing for the whole set of layers, okay? So that we can keep the common functionalities in a single module and then obtain the specialized function using derivation. In this case, we are showing the part from the structural point of view, but the same thing is made from the class C++ class point of view. Okay, as I said, the main goal is to test algorithms and in particular results scheduling algorithms. But for doing so, we need first to model resources, to model resource management, so how the system deals with the resources, and possibly providing an API to the users, which are the first user of the simulator, so as to implement new functionalities on it. Quick overview of what happens at the transmission reception side. LTE is based on a technology which is called OFDM, which is pretty complicated when you look at it down to the signal level, but as a cool thing that you can easily draw a picture of that, because it's simply over 1 millisecond we have the frequency, that is the bandwidth of the system, which is divided in chunks of a certain amount of symbols. Those chunks are called resource blocks and are the basic allocation unit of each LTE scheduler, every LTE scheduler or algorithm in general. The work of the scheduler is that for each millisecond he has to assign those resources to the user that are available at the moment. And has to do that over time, millisecond by millisecond. The interesting thing is that each resource block will contain a number of bits that depends on the channel quality that's perceived by a single user. So you will find the classical problems like ensuring maximum throughput or ensuring a minimum delay or ensuring fairness for every user. And everything will depend on actually how many blocks I will give to a kind of user depending on its channel quality, which by the way is called CQI. So, in order to support this, we implemented a module within the MAC layer which is responsible for, not the module, actually a class structure that is responsible for managing scheduling. And for example, we have the scheduling policy that receives data and data requests from user of the upper layers. And we have the AMC module, which has the UE reports, which basically are those CQI that we talked about 1 minute ago. So the channel quality, information on the channel quality. And these information are communicated to the scheduler so as to tell the green user can fit n bits in one resource block, whereas the blue one can fit n bits. And the scheduler can allocate such resources to certain user by using the allocator, which is a module that keeps track of all this stuff all together in one place, and just write a schedule list. Okay? So basically the user which is going to write a different scheduler will just work on this piece and use the interface with this guy. Okay? So every other element is hidden. And this is performed the following way. We have a common structure for the scheduler, which was a big block that was defining all the data structure and functionalities that were common for both transmission direction, and we specialized two versions for the uplink and the downlink direction. But again, what any user has to do to perform a new scheduler is just inheriting and implementing a new scheduling policy. Is what we did for those well-known scheduler, maximum throughput, proportional fairness, or deficient route and the same thing that can be done by any other user. Okay, we are in time. So, once all of this is in place, I will try to discuss with you how we can implement some kind of LTE example, actually 3 LTE examples that have shown up over time. We start in, please take the dates with a grain of salt, because those are actually not the date that the release was started or created, but just the period in which those technologies were actually thought about. So in 2010, LTE releases are called in fact releases. The first two were 8 and 9. Why are they starting from 8? Because the previous one were for 3G communication, and we are talking about 4G communications. The first type of networks that were available were simple cellular networks with user equipment deployed around, for example, a city. This is an exemplary deployment of LTE in Budapest. And we can see the common nodes that we talked at the beginning of this talk, which are the eNodeB and the user equipment. Also, we have pretty well-known nodes coming from iNet, which are the channel controller and, for example, the address configuration, the routing recorder. And also, we have this guy that is called Binder, and has similar functionalities to the channel controller, but from the LTE point of view. And also, as I said at the beginning, we have on top here kind of an example of network that is connected to the LTE network. What can we do with this? Of course, this is a simple network. We can manage the common parameters, which they come from iNet, and all of these nodes, for example, has a mobility module within them, so we can change the way they move. We can change the application type that is on top of the layer, and we can also change strictly LTE related parameters, such as the number of resource block, so the resources of the system, which scheduler is being used. This is a very simple code snapshot. For example, the first thing that we need to do in this case is associate users to the actual cell that is used. We have two parameters because one is associating the user to the cell, which is the space here around the zone. And the second one is the master ID, which is the name of the eNodeB, which is serving it. It's just a reason for flexibility because we may have such a little bit different cases. But just for now, those elements are the same. Then we can specify the amount of resource blocks that are being used. They can be made in a pretty simple manner. And for example, we can select which is how to configure the channel, because I didn't talk about this, but underline we have a channel model that it deals with signal propagation, and we can change the behavior of this XML file. And finally, we can, of course, select the scheduling discipline, which is a parameter of the MAC layer. Okay. As I said, if we would like to implement a different scheduler, we just have to inherit the scheduling policy and define a new one, and just define two new functions. The scheduling is performed in the two-step method. The first prepares the scheduling list, which can be stored somewhere within the simulator, and then it's just committed at the end, or when everything is ready. Why are we doing this? Because so as to let a user, for example, to test multiple schedulers within the same millisecond time frame, and then just so preparing different scheduling lists and then just committing only one. Okay, it's just a way of testing different scheduler within the same time frame. Okay. If we move to the next period, we are in 2013. We are moving to release 10 and 11, and we are talking about something that is called LTE Advanced. That's evolution of LTE. The new concepts are using a lot of different cells within the space, and using something that is called coordination, multi-point techniques to coordinate those nodes, and using something that's called X2 communication to let those inode Bs communicate all together. We will see why we are going to do this. Basically, there are two concepts in this context, which are the heterogeneous networks. That means that any of these nodes can have different power levels. For example, the concept of femtocell, picocells, which are developed in small places or within houses. And there is another concept of dense networks, which are basically adding a lot of inode Bs in space with the goal of satisfying the request from hotspots. Okay? So these are the concepts that were getting out. Some of the concepts that were in release 10 and 11. What we did here is try to model these problems. First of all, with me? Yes. Again, we need to associate each user to the corresponding inode B. We can do similarly as we did before. Okay. So setting for all the users with this name pattern to, for example, inode B number 1, and so on and so forth. Then we can change the transmission power at the physical layer by varying this parameter. This, of course, will change the channel quality which is perceived by the other user, but will also have side effects. What kind of side effects? Interference. What happens here is that LTE, the old LTE network as a whole, uses only one frequency in general. Okay? So what happens is that nodes are interfering each other, and we have to take this into account in normal scenario, but especially in heterogeneous configuration and in dense configuration as well. So what we did was adding the management of something that we call multi-cell interference that can be set in the config channel that we talked before, and it's something that we can enable or disable just for testing purposes. Okay. And we will see how can we deal with this problem. In fact, the main question that comes from this scenario is that we have a lot of interference, how we can deal with this. And the answer is that we should coordinate those nodes using the COM technique, okay, coordinated multi-point, which is basically as the idea of not looking at a single inode Bs, the allocation of inode Bs, so the little square that we saw before, but taking a look at all of them all together and trying to coordinate the allocation of the whole set of schedulers. For example, trying to avoid nearby inode Bs to use the same frequencies, or for example, doing completely different allocation over frequency, and this not has to be done on a 1 millisecond basis, okay? Because we need to coordinate those scheduling on a 1 millisecond basis, okay? In order to do so, we try to give a little bit of flexibility to the end user, and what we explained before was the classical inheritance of the scheduling policy, which is able to communicate with the allocator, which is again responsible of taking care of all the resource blocks that are allocated, using a simple function that is called get blocks. Okay, so the scheduler basically asks the allocator, give me 3 blocks for that user, and the allocator, if he will allocate this. This is, as we can see, the most as user-friendly as possible, but lacks a little bit of flexibility. A second solution that we talked about was to use, again, the same scheduling policy manner, using the get block function, but adding a limit. which is basically saying to the allocator, okay, I need 3 blocks, but please do not give me any blocks within this limit. For example, block number 5 and now block number 10, because I know from coordination that those blocks are already allocated. Again, this is something in the middle of between user friendliness and flexibility, and the maximum flexibility that can be achieved is making scheduling and allocation in a jointly manner. Okay, it's a lot more complicated because we need to directly modifying the allocation of resource blocks within the allocator itself. Okay, so we are actually giving these different possibilities, and we are doing so because in general we will have a kind of a coordinator somewhere in the network which will actually decide the schedule for the whole network and then guide the decision of the single schedulers. Okay, so algorithms like this need to be tested and need to be tested on a large scale. So I normally receive the same question every time I do a presentation about SimuLTE. It is something like, how many node Bs can you simulate with your simulator? My answer is generally we test until 9 or 10 node Bs with 1,000, generally 1,000 of user equipment. So we are able to make a pretty good large network. The main problem is that is enough as for a source of numbers to achieve a good statistical soundness of results. But what if we need to obtain larger observed side effects, or what are called border effects around the cells? So we introduced the concept of lightweight node Bs, which are, again, simple modules that are mimicking the behavior of node Bs. They are not implementing the stack, they are not serving actual user, they are just allocating resource blocks. Okay? And we did so that the behavior of these node Bs from an external point of view for the rest of the network was exactly the same. Those can be easily configured using ini files. They share the same parameter, physical layer parameter, as for the other node Bs, so we can decide the transmission power, the transmit direction, whether it's anisotropic or isotropic. And we can select the way they allocate resources. For example, we can randomly allocate 50% of the resources, or we have other modes like just take the allocation of all the average allocation of all the other node Bs and just add some kind of perturbation or stuff like that. And we can, of course, manage the positioning. Note that this is not made using the mobility from INET, but because we do not actually need to move those objects, but we use actual very light nodes that can be moved from just the point of view of the LTE network. Okay. Concerning this, there is another point. As I said, if we need to implement a coordination mechanism, we of course need to let those nodes communicate. Okay. This is made with the standard LTE standard defined an interface. This is called an X2 interface, which is physical layer agnostic, so it can run on fiber, it can run on Ethernet or ADSL, whatever. And we implemented this protocol actually, adding to the side of the LTE NIC card an X2 manager. And just to let you understand the context, the coordinator we talked about is just a user of the X2 interface. So the guy that will coordinate all those nodes might be, for example, this node B will coordinate all the other node Bs, will be an application running here that will be able of communicating using X2 interface using other interface outside here, and making, of course, cross-layer operation with all the other layers. Okay. So basically we did this because if you need to implement a different coordination scheme or any kind of application that will need to cooperate with other nodes, we just need to extend to implement an application right here. This is how you can configure the X2 interface. It's pretty simple and can be done, of course, via ini files. Okay, any questions so far concerning this? Okay, this is the final rush. This is the last snapshot of the LTE history. Something that is actually something that's happening since 1 or 2 years ago, and is moving toward the definition of the 5th generation of cellular networks. And I will target specifically one topic among the lots of topics that are within 5G. What we talked about till this point is that we have user equipment that are communicating with the internet, either in the uplink direction, so from the user toward the internet, or the opposite direction from the internet toward the users. We can also have communication between user equipments of the same, for example, for the same network, but all of this communication will need to go through the node B. Okay, so the node B will always act as a proxy of each communication. But what happens if two users are near each other? So in this case, it will happen something that is pretty similar to the first presentation that we heard about after lunch. We can exploit something that is called D2D, so direct communication, user-to-user communication. Those communications may happen in the classical two ways that are pretty known in the communication topic. They can be multicast, or more in general broadcast, or they can be unicast. Okay, and those are the two modes that are foreseen for D2D. Actually, the standard is just defining the multicast one, but I think everyone in the community which is working, in the research community which is working on D2D, at least talked one time about unicast D2D. There are plenty of papers concerning unicast D2D. What does it change? Basically nothing. The scheduling remains under the control of node B, so the node B is still controlling who's talking to whom. And user equipment still need to request resources to the node B, to the node B itself. Okay, so the only thing that changes is that the user equipments are talking directly. This implies that probably these two user equipments will have better channel quality and will probably end up having a less delay because we are cutting one leg of the communication. And last but not least important, we have the possibility to enable frequency reuse, because those communications will occur at using a smaller, lower power transmission power, and will possibly create less interference to the other users. Okay, so within this topic we have to change. Are you with me? No? Okay, old-fashioned way. We have to slightly change the behavior and the way the layers communicate. We saw that in normal unicast communication, the data was traveling from one layer to the other using gates, okay? And all the classical operation like segmentation and concatenation or error control were performed by each layers, using a reverse path on the other side, on the other direction. When we deal with D2D, we had to add a different data path. Why? Just because as soon as the data is entering the LTE stack, we have already to know where it should go, because the numbering of the segmentation of the flows or the packets has to change depending on which leg we are using, and also the HRQ, which is a simple automatic request control, which is simply a ACK-NACK based transmission method, has to be separated for those directions. And the main reason for this, we will see that in a minute, is that we will be able to decide whether we want to keep the connection between the two users in a direct manner or in an infrastructure manner, so passing through the eNodeB, depending, again, on the channel quality, on the data request, on the interference. Okay? D2D is managed again, can be managed again from INI files. Of course, you have to include the suitable modules within the LTE NIC card on the user equipment in general. We can enable or disable D2D at the beginning of the simulation. We can decide which type of AMC mode to be used. The AMC was the model that was responsible of controlling the channel quality of the user, and we have to set that to D2D, because in this case the eNodeB has not only to know about the channel quality between the user equipment and the eNodeB, but also between the user equipment and the other user equipment that is peering with him. We also have to establish peering relations, so that we have to tell the system which pairs are actually eligible for D2D. This is something that can be modeled in a complex and dynamic manner, which actually is not available because we are not doing research on this. Because according to the standard, there is a node somewhere in the very complex LTE core network which decides whether two nodes will be D2D capable depending on some kind of capabilities. So this can be changed, can be foreseen to be changed dynamically. And for the moment, we have to establish the peering relation by telling the name of the module to which one user equipment is peering to. And finally, we have to select and to set some kind of channel related stuff. In particular, we can still decide whether the channel quality will be sensed by users or not. And for example, in this case, we are telling the system to work in a classical manner. So users are measuring channel quality and are measuring CQI, so the channel quality dynamically, and reporting that to the eNodeB. And we will see that is not the only way to do that. We will see that in the following. Finally, we can change the transmission power of the user equipments of either the transmission power in infrastructure mode or in D2D mode. So we can have the two different transmission power depending on the mode. Okay? Because as I said, if my peering user equipment is close to me, I can lower my transmission power so as to save, possibly save batteries. We are not investigating on this, but it can be something that can be studied. And we can also reduce the interference to the others. In fact, what happens in such a scenario is that all user equipment can reuse the same frequency. Okay? For example, let's suppose that with this case, all those pairs, all these pairs are communicating using exactly the same frequency. What will happen is that if a transmitter is close to another receiver, it will generate interference on that, okay? Because LTE transmission are wireless transmissions, so are intrinsically broadcast, so the interference will be received by all the other elements. And for example, it may happen that one pair is really close actually to the eNodeB. So we may decide, as I said, to switch between the D2D mode to the infrastructure mode. And we may decide to do so dynamically, depending on the status of the channel, the data request, and so on and so forth. So for this reason, we can also decide whether two pairs may or may not transmit simultaneously. So what we are doing basically is introducing problems that need to be solved by algorithms. And again, we have the classical resource scheduling problem, which is selecting who is talking to who in which resources, and is a typical example. But we also have the problem of selecting which mode each pair has to use, okay? And we may want to do that dynamically. How can we model this problem within our simulator? Remember that data are sent in unicast, so we have only one target in this case, but the interference is still broadcast. And during the infrastructure case, what we did was that, you remember that nice picture of resource blocks? We were basically coloring those blocks and tagging each block with the name of the user that was using it. But what happens in this case when we have multiple users that are transmitting simultaneously on the same resources? We have to change that model to something like this. So every resource block within the space, the frequency space, has to be tagged with can be tagged with a list of user equipment, okay? So that when we compute the signal to noise interference ratio, we know exactly how many and actually which user are transmitting on which resources, okay? This way we can have a pretty good approximation or evaluation of the actual interference that's happening. Okay, I will skip this one. We are basically defining, similarly to the definition of the scheduling policy, we can do the same for the mode selection. So we can define a new mode selection algorithm by just inheriting that class over there and implementing the do mode selection function, which is pretty simple. And the last thing I would like to talk about is the other way around, the multicast version of D2D, I think we recently published that online. The idea is pretty simple. Each user can communicate with all the other users in range, using, of course, the capability of broadcast communication. And we can do this by just configuring a multicast address within the XML configurator file, if I remember the name correctly. So we are basically telling to the address configurator that we are a certain set of users belongs to that multicast group. We need, of course, in the ini file to set as a destination address that multicast group. And then we have to set the same parameters as before. In this case, however, we cannot use the CQI measurement. Why? Just because we have multiple receivers and we are transmitting the same message to all those receivers. So we have to use the same modulation and encoding scheme. So we cannot change the way the data is actually modulated by the physical layer. So in that case, we are basically using a static transmission parameter, and we are selecting, for example, in this case, CQI number 7, which will mean that in one resource block will be at maximum 40 bits, for example. And finally, we can still select those physical layer parameters, so transmission power. And okay, already told about this. Why do we need to configure the CQI in this case? Because we can, for example, if this node, UE number 4, is outside of the transmission range of user equipment number 3, we may, for example, increase the transmission power. But of course, this will lead to other problems, interference problems and stuff like that. The other thing that we may do is we can change the CQI, for example. I do that on the opposite way. For example, if we use a lower CQI, for example, CQI number 3, it means that we will use a more robust modulation, which will lead to basically a larger transmission range, but also to lower data rate, okay? Because if we have a lower modulation scheme, we are basically changing the amount of bit that we fit within one resource block. It will mean that a lot more of you, more user will be able to decode the message, but it will also mean that we will have a lot less data within it. And same thing for the other way around. Okay. Last thing, we have to change, to give another separate path to the D2D multicast, just because in the case of multicast we do not have the automatic repeat request mechanism, because we cannot have multiple ACK and NAC from multiple users. And in this case we have to use the send broadcast, which is basically the same as for the iNet version. Currently it still works by sending the message to all the users that are in range, but it might be changed by just including so maybe it's only the users within the single cell. Okay, I think we are running out of time. We are still working on something. We released Andover recently. We are working on providing native support to VANs, which is the technology for the model for vehicular communication, which is actually available, something that is called SimuLTE, I think, that is SimuLTE all together with VANs. We would like to merge all these within SimuLTE so that we have only one thing that can be improved just one time. And we are still moving in the direction of 5G communication with the novel CRAN cloud deployment, which are models deployment based on clouds, and moving towards mobile edge computing, which is a new paradigm. It's pretty similar to fog computing, if you are familiar with that, but in the field of cellular networks. So, concluding this pretty long rush, we talked about SimuLTE, which is a simulator focused on resource scheduling. We talked about layering, the modeling of resources, and the scheduling. And we described a few case studies from simple LTE networks, passing through LTE Advanced, and finally to direct communication. And that's really all. Thanks for your attention. I hope you at least survived to this tutorial. If you have any question, you can ask me right now or maybe during the coffee break, which I suppose we are having right now. Okay?
So,
thanks a lot.
Very, very big. I'm just going to release you into the coffee break where you can, I'm doing one of the developers of SimuLTE, everything about SimuLTE, LTE itself, and I'm going to take some later, okay? That's some homework, but later on.
I will ask the presenters for the next session if they can stay by me and tell me their names. Anything that should I know before.